Okay, let's get started. Again, I'll switch to English. Thank you for the invitation, for giving this talk. It's always wonderful to talk to students who are excited about learning about cutting-edge topics. And I appreciate that I was invited to give this talk to students in Turkey who are interested in doing good things, I think. So I'm going to talk about future computing architectures, which is my specialty. And I'm going to talk about some challenges and opportunities. Feel free to write any questions so that we can answer them at the end if you're interested. Let me very quickly introduce myself. As mentioned, I'm a full professor at ETH Zurich for about 6 years now. Before that, I was a professor at Carnegie Mellon University for some time. I got my PhD from UT Austin and worked at many companies. I started the computer architecture group at Microsoft Research in Redmond after my PhD, and then moved to Carnegie Mellon. But I worked at many companies like Google, VMware, Intel, AMD, and I still work, my group still works closely with many companies in terms of the future computing architectures, which is the subject of the talk. If you have any interest or questions, you can feel free to email me, or you can look me up on LinkedIn or YouTube. I will mention the YouTube channel in a little bit. I do research and teaching in computer architecture, computer systems, hardware security, and bioinformatics. These are some topics that we're going to talk about. Hopefully, they will be interesting. These areas, I believe, are the leading areas that have enabled the machine learning revolution today. For example, if we didn't have the capable hardware architectures to enable very efficient and fast training and inference, machine learning would not be a big application today. And we are looking into future applications in our research. We're looking at the genome analysis, for example, which I will hopefully get to talk about. So I will continue introducing our group a little bit and our work, and hopefully that will be a good introduction to the talk also. I'm going to talk about, basically, we work on building fundamentally better architectures. And architectures include all of the components of an architecture, basically processors, graphics units, memory, especially memory, persistent memory, and also the macro scale architecture, where you connect these things together so that you can form an even more powerful network of computers or multiprocessor systems. We work at the hardware-software interface, systems, bioinformatics, and security. And these are all exciting topics to me. And these are 4 current directions that we are following. I'm going to probably cover only 2 of them because we don't have enough time to cover all 4 of them. But you will find slides in this talk that cover all 4. We're looking into designing fundamentally secure, reliable, and safe architectures because it's going to be critically important to design very secure, reliable, and safe architectures because we're going to rely essentially everything in our lives to computing platforms of the future. And if they're not secure, reliable, or safe, basically we will be at risk of many, many problems. Then we're going to talk about fundamentally energy-efficient architectures, or in other words, memory-centric, data-centric architectures. This is going to be extremely important also because, again, sustainability is a huge problem going into the future. We have a huge climate problem that is threatening the future of human life on Earth. And I think we need to solve that problem intelligently. And computing is going to be an important part that plays a role over there. We also work on fundamentally low latency and predictable architectures. I think this is important. Again, when I press my cell phone, I want predictability from my system. And this is going to be even more important for life-critical, safety-critical applications like self-driving cars, for example, that we're going to rely on in near future. And who knows, maybe flying cars or flying systems that are going to be around taking us into the space. And predictability is going to be very important, and low latency reaction is going to be important. Probably we're not going to have time to talk about this third portion, but I'm happy to point you to important works that are going on in the area. We also work on architectures for artificial intelligence, machine learning, genomics, medicine, and health. And I think these are really emerging and critical areas for humanity going into the future. I'm going to briefly touch upon this. We have a lot of work on this topic, but I probably won't have time again to talk about this in detail. But let's get started a little bit. And I will mention that this is the transformation hierarchy that we have built. Basically, we have problems and we want to solve them. And we build computers to solve the problems. Essentially, the job of a computer or computing system is to transform this problem through this transformation hierarchy such that the electrons can solve the problem for us. And if you look at computer architecture, traditionally it's been defined as the interface between the software and the hardware and the microarchitecture that implements the specification, that interface essentially. But I take actually a much wider view of computer architecture, in fact, all the way from algorithms to devices, so that we can solve the problems with a computing platform very efficiently. And that I call this the expanded view. And I think I'm going to assume this view in the rest of this talk, because we need this view to achieve the highest efficiency and performance, as well as security, latency, predictability, etc. We must take this expanded view. Basically, we must co-design across the hierarchy, take our algorithms at the software level and adapt them to the devices that are executing them at the lower levels, and also co-design algorithms and devices together. I'm going to show you examples of this, and specialize the system as much as possible within the design goals. If you want a fully secure system, it has to be secure all the way from algorithms to devices. If you have a problem somewhere in between, then your system is not going to be fully secure or safe or reliable. As a result, your self-driving car may crash very easily, for example. So you want the whole system to be secure, for example. And that's security is one example. Efficiency is another example. If you want a completely very efficient and extremely fast system that can take your machine learning workload and do it extremely fast at high efficiency, again, you cannot say, oh, I have a great software for this. It's not going to work. You really need to co-design the software, algorithm, languages, hardware-software interface, microarchitecture, logic, devices, all of them together, so you have the full package, full computing platform. And I'm going to give you examples of this also. I'm going to skip the slide, but this slide goes into a little bit more detail in terms of the research areas that we're working on. I think it's not as important at this point, and I'll give you examples. This is my research group, and I'm going to present work that has been done essentially by the current students as well as the past students in my research group. If you're interested, you can read our newsletter that is on my research group's website, and you can find it over here. I will put these slides up on my website sometime after the talk, so you can find all of these links on my website. So I will briefly mention about my mentality in terms of how I approach education and research, so that you understand what's coming next a little bit better, I believe. And also you understand my personality a little bit better. So I strongly believe that teaching and research drive each other. Essentially, these are two sides of the same coin. In teaching, you educate people about things everybody knows, assuming everybody knows what they're teaching, right? In research, you educate people about something that people didn't know before, only you know, basically. And after that, research becomes teaching, and then these things drive each other as a loop, basically. And I very much use examples from cutting-edge research in my classes. So if you look at my online classes, you will find that I introduce students to the cutting-edge research ideas, even in my freshman class, which is the first year of school at ETH, Introduction to Computing Systems class, essentially. And I believe this is really important. We really need to incorporate cutting-edge topics in our research, in our teaching, so that we can actually motivate people to do something bigger, something new, as opposed to keeping the topic stagnant over time. The other thing that we focus a lot in my research group is insight. Basically, we care a lot about new ideas, generating new ideas, and generating new insight that people didn't know before. And that's how the world improves, right? Once we stop generating new ideas, then the progress stops in the world. Once we stop generating new insight, progress stops. So it's really critical to have a culture that keeps generating insight, valuing insight, and values new ideas going into the future. So if you want to know more, we put out a lot of information on our YouTube channel and also on our websites on the talks that we have delivered, as well as the lectures that we have deliver both at Carnegie Mellon and at ETH. And you can find them on my YouTube channel over here. And these are some example talks over here. And if you're really interested, there's an interview that I delivered to 2 students in 2019 who asked very, very good questions about research, education, future of computing, etc. And if you want to know my views on it, you can find that at this YouTube link over here. And if you want more thoughts and suggestions, there's a lot of material we have online as well on how to build an impactful research group, for example, that I deliver once in a while as invited talks at top conferences in the field. And anything that I reference in this talk, you can find online. We put out material. I believe in open sourcing information And you can find all of the material online on my website, as well as on our GitHub site, and as I mentioned, on our YouTube channel. Now, with that introduction, let's jump into the real topic of this talk, which is future computing architectures. And I call this challenges and opportunities because I talk about both challenges and opportunities going into the future. And I will start with one key question, which is, why do we actually do computing? And I think that's a very important question that we should ask ourselves once in a while, so that we get ourselves on the right track, because I think sometimes we go off the wrong track and try to use computing for purposes that are malicious, let's say, and not so important potentially. So we should probably steer ourselves by asking this question once in a while. And I think the answer is to solve problems, basically. We would like to solve problems that we have, and that's where computing can be most useful. And to reword this answer, I should say, we would like to solve problems by gaining insight to those problems. And this was actually what Richard Hamming, in his seminal work, mentioned also. Richard Hamming is known for Hamming codes, for example, and this is the work that he wrote related to Hamming codes, numerical methods for scientists and engineers. And he said that computing is all about insight, not numbers. So if you extend the answer, basically, you would like to enable a better life and future for us and everyone, hopefully, over the world. So the question is, of course, how does a computer solve problems? And the answer is by orchestrating electrons. In today's dominant technologies, we need to tell the electrons to solve our problems. Of course, it's not easy, because we cannot communicate with the electrons, right? That's why we build a transformation hierarchy. We have a problem, and we want to use the electrons for our purpose to solve the problem, but we cannot speak the electron language, and electrons don't speak our language. Once we solve that problem, that'll be very interesting, I think. So we have to build a transformation hierarchy where we express the problem in terms of algorithms, and then program them in a language, and then that gets executed on some sort of system software and the hardware-software interface. That gets implemented by microarchitecture and logic gates underneath, and devices which are composed of electrons in the end. So as I said, the narrow view of computer architecture looks like this, but today we are way past that narrow view. We should really be thinking about co-designing full systems, algorithms to devices all the way, so that we can get the highest efficiency. So let me give you what the definition of computer architecture. Computer architecture is really the science and art of designing computing platforms, hardware, interface, system software, and the programming model, essentially. And I'm going to give you examples of this. Basically, the goal is to achieve a set of design goals. And the design goals could be, you would like to get the highest performance on Earth on workloads X, Y, Z. Let's say those are really important workloads. This could be designing a supercomputer, for example. You may want to get the longest battery life at a form factor that fits in your pocket with low cost. This is an example of a mobile system, a cell phone, for example. Or you may want to get the best average performance across all known workloads at the best performance cost ratio. This is a general purpose system like what Intel and AMD have been building, like a laptop or a desktop, right? And these are very different design goals, clearly. One is trying to achieve good performance across all workloads, and one is trying to achieve extremely high performance on a few workloads. And you can call that very specialized, but these are different design goals. And there could be many, many other architectures, as we will see in a little bit. So in the end, designing a supercomputer is different from designing a smartphone, because you need to exercise different trade-offs, but many fundamental principles of design are actually similar. So if you're designing a system for a bank, and if you're trying to make it secure and efficient, etc., you're going to employ some principles, and those principles will have some similarities to a supercomputer or a cell phone or a laptop. But then the trade-offs using which you exercise those principles will be different. So essentially, you can take your own problem over here. If you're designing a supercomputing center at a university in Turkey, for example, you might use similar principles but exercise different trade-offs. So I'm happy to talk about it. And if you're really interested in different types of computer architectures, I'd recommend you take a look at the courses in my YouTube channel. So let's take a look at these different platforms. Clearly, these are platforms that all of us use, I believe. This is another platform. This is actually a computing platform. It's a flying computing platform. It has to be extremely efficient. Clearly, it has different design goals. This is another platform. And I wish our platforms were as good as what Mr. Bean relies on. So I don't think self-driving cars today are at a stage where we could rely on self-driving cars so that we could sit at the top of them. But maybe that's a good goal to achieve going into the future, right? And this is another computing platform. This is one of Google's self-driving cars. You can see that there's a lot of machinery in the back of it, a lot of servers that enable it to actually move forward without hitting something, right? So it's going to be, the key is how to make this much, much more efficient going into the future while keeping the security, reliability, and safety. This is another platform. This is a data center. And you can see that it can run many, many workloads, and it's designed in a completely different way. But again, fundamental principles are similar. This is another platform, completely different from the data center, but looks similar. This is a supercomputer. That's one of the fastest supercomputers of its time, Tianhe 2 from China. And it's extremely good at executing some supercomputing workloads, high-performance computing workloads. And there are very few of them comparatively to all of the workloads in the world. This is another platform that Google designed. It's called a Tensor Processing Unit. It accelerates machine learning applications and Google decided to design this platform so that they could accelerate the machine learning that they do in their data centers. And imagine Google, like you think of Google as a software company, but they're designing their own hardware platforms. And that's happening all across the world today. These software companies, they're finding that it's very difficult for them to design systems that are efficient and high performance enough without designing their hardware. So they start designing their hardware. And this is one of the earliest machine learning accelerator chips. It operates based on systolic array principles. You can read this paper or watch my lectures on systolic arrays if you would like to learn more about it. But basically, it's extremely good at doing matrix multiplication. So the unit on the right over here can do, I believe, 64,000 multiply and add operations, which is at the core of the matrix multiplication, which is at the core of machine learning, inference, and training, essentially. And this chip is composed of many of these units, if you will. And it's called a tensor processing unit. This is another example. Google actually has another generation I have in the later slides, but you can take a look at the slides if you would likely not to get to that. Another example is from Tesla. This is Tesla, which is a car company. It has nothing to do with hardware chips, as you can see, but they designed their own chips, again, for the same purpose, because they found out that the chips that are out in the field are not good enough for their purposes, because they know their software, they know their cars, and they want to make sure that these chips are co-designed together with the software and the cars so that they can actually make sure that the system is completely efficient and high performance. And you can see that these chips are very extensive in terms of what they can do. Lots of transistors, lots of floating point operations. They also have CPUs as well. And they also have two of these chips so that they can provide better safety. So safety is a critical concern that they have in a self-driving car, clearly. So if one chip does something wrong, the other chip doesn't agree, then they figure out that there's a problem. And this is the fundamental principle of dual modular redundancy that's employed in many safety critical systems, of course. Of course, if you really want to be even safer, you would like to increase the safety margin by adding more chips, for example, that do the same computation multiple times. This is another example that has happened more recently. This is in 2009. This is a wafer scale engine. You can see that this is the size of a largest graphics processing unit, which is used for machine learning applications. And graphics processing units have actually driven the machine learning revolution. Machine learning algorithms were designed in the 1980s, late 1970s. But people figured out that these algorithms are extremely hardware intensive until 2012. In 2012, folks from University of Toronto, Jeff Hinton's group, for example, showed that you could actually train these machine learning models extremely fast with GPUs so that these algorithms became competitive. As a result, the machine learning revolution, as we're experiencing today, has started because there was a platform, hardware-based, that enabled that machine learning algorithm to actually be trained. That was a GPU. But today, a GPU is not enough. Today, we have such large machine learning models that can do a lot of different predictions, classifications, natural language processing, etc. And the size of a GPU, the computational power, is not enough. So these folks, this is a startup called Cerebras, they designed a wafer scale engine. As opposed to taking a full wafer and breaking it into smaller chips, they said, we're going to have the full wafer as a chip. And you can see that this has 1.2 trillion transistors and more than 46,000 millimeters square. So this is like this. If I was holding it like holding this chip, it is exactly like this, basically. It's a big chip, essentially. And you can see that today's applications are straining the boundaries. As a result, people are designing these innovative designs that are going to be very interesting going into the future. And you can see the number of cores over here, 400,000. Okay, this is another exciting platform. This is a processing in memory engine. Usually we think of memory as something that stores data, but That's not true anymore because startups all over the world, this is a startup in France, UPMEM, it's called UpMem, they basically have designed a memory chip that can also do computation. Basically, you can put some computation next to the memory so that the data from memory doesn't move all the way to the CPU or the GPU. And as a result, your processing becomes extremely efficient because data movement is actually one of the most power consuming and performance consuming things that you can do in a computing system. This way you can eliminate a lot of data movement. And we actually work with this company. We evaluated their system with our own workloads, and we see that this can perform very, very well compared to state-of-the-art CPUs and GPUs. Now, recently, this is another example. We've been working on processing in memory for years, almost 8-9 years right now, actually close to 10 years, I believe. But basically, recently, Samsung announced that they're building their own processing in memory chips to accelerate AI or machine learning applications. And you can see that their new processing in memory architecture brings powerful AI computing capabilities. Clearly, this is a marketing post over here, but you can read more about it if you're interested. But essentially, what they do is very similar to what we have been working on, essentially putting processing inside the memory or near memory. And you can see that they accelerate core operations that are at the heart of machine learning. Again, multiply and accumulate, and multiply and add. And as a result, if this becomes available, which hopefully it will, it's going to be important for future workloads. So another workload that I mentioned earlier is genome sequencing and analysis systems. There is no specialized chip for this purpose. We're actually designing some of the specialized chips for genome sequencing and analysis. But going into the future, I think this is going to be perhaps an even more important workload that is going to affect all aspects of our health and medical innovations in the world. And you can see that there are already some systems that can do the genome sequencing with very small hardware. This is Oxford Nanopore Systems, ONT is the abbreviation. And you can attach them to your cell phone. But unfortunately, the computational power of a cell phone is not enough to do the processing on a genome and to answer the questions that you would really like to answer whenever you take someone's genome. And let's say you have a life-critical situation where the doctor takes someone's genome and they need to answer the question, what kind of drug should I administer to this person so that I can save this person, right? And you don't have time in this case. You have to make a decision within, let's say, 2 hours. We would like to make this decision within a minute or even less, actually, within seconds. Today, that decision takes days and days. So today, we don't have enough computation power. But in the future, hopefully with algorithm architecture, hardware device co-design, we can design these systems that can enable much better medical care, much better healthcare, and much better scientific discoveries going into the future as well. So if I don't get a chance to talk about genome sequencing and analysis work that we're doing, this is the basic summary. Okay, so I've already said the axiom, but basically to achieve the highest energy efficiency and performance and security, reliability, etc., we must take this expanded view of computing architecture and co-design across the hierarchy, algorithms to devices, as well as all of the layers in between, as you can see over here, and essentially specialize as much as possible within the design goals that we have. Okay, with that, now I've given you an overview of computer architecture today, if you will. Let's talk about the future, because always we should be focused on future. And if you want to have a good future, we should innovate. Without innovation, I think life stops, essentially, or it becomes boring, not interesting. Innovation is really what we really want, and that's what science and engineering can enable us to do. But of course, we need to drive the innovation in some way. And the question is, what kind of a future do we want so that we can drive the innovation in a good way? So I will point to some key important things. I think reliability, security, and safety are really critical. So if you look at this bridge, this is critical infrastructure, right? It connects two pieces of land. And if this bridge fails for some reason, then you have a big reliability, security, and safety problem. This is the Tacoma Narrows Bridge. It's over the Tacoma Narrows. It's in Seattle. It's close to Seattle, where I used to live when I was at Microsoft Research. And basically, this bridge had a fault. And 6 months after it was constructed, this is what happened to it. It basically broke. It was called the Galloping Gertie, but it was doing like this for 6 months or so. And I consider this as a bit flip, but it's a problem in critical infrastructure. And you can see another view of this bridge after it was destroyed. And I think we do not want this sort of problems in our critical infrastructure. If you think of bridges, they're important. But if you think of computing devices and platforms we use today, they're much, much more important. because we have billions of computing devices already that are part of the world. And some of them are making important decisions for our lives. And increasingly, more of them will be making important decisions for our lives. And if they have this sort of problems, then we're going to suffer a lot going into the future. It could be life critical. It could be actually really bad if it happens in a self-driving car. So we don't want security, reliability, and safety problems happening across the computing devices, which is perhaps the most important critical infrastructure of systems that we build today. Human beings have been building bridges for thousands of years. We've been building computers for tens of years, but computers have already overtaken the bridges in terms of their importance, let's say, because they're employed in all aspects of our lives. Right? So another example that I give to my students when I talk about security in my first class in the freshman year is this rod. Basically, these folks who are constructing New York after the World War are happy right now because they're on a steel rod. But what if that steel rod has a bit flip? It's not reliable. They will not be happy very soon. So I think of security in a broader sense. I think of security as about preventing unforeseen consequences. So we need to think ahead. We need to design our systems such that they will we put stuff in them so that they will be operating under the assumption that they will not be reliable, they will not be safe, they will not be secure, and they will be on the lookout for these unforeseen consequences that are all around them so that they will make them fail. So if we have this mindset to building systems in terms of security, safety, and reliability, then we will design systems that can adapt much better to these safety, security, and reliability problems. So I think a huge challenge and opportunity for future is designing reliable, secure, and safe systems. And this is going to be even more important in the future. The second challenge and opportunity, I believe, looks like this. Basically, do we want a world that looks like this, that is beautiful, sustainable, no climate problems? Or do we want a world that looks like this? Of course, this is an example from the past. In the future, this may be even worse. I would argue that we would like sustainability and energy efficiency, and this is a big challenge and opportunity for the future. We would like complete energy efficiency, but we would like to have the productivity of a world that looks like this. We would like to have performance as well, and that brings me to my next point. Today, we have many, many difficult problems to solve. Climate is really important. Climate modeling is also actually very tough. Congestion is a big problem. If you're living in Istanbul, for example, you will know that, but this is a picture from China, and it's very regular compared to Istanbul. I think Istanbul is quite irregular. Another problem, even bigger problem, I would say, is intelligence. Can we understand the roots of human intelligence and human behavior by modeling it, by doing computing device, and can we imitate it? Another problem is public health. Going forward, actually, it's going to be even more bigger. We were working on bioinformatics for more than 10 years, actually almost 14 years now. But today we have huge public health problems like COVID-19. And this is not going to become better. It's going to become worse. So we would like to build computing systems that can understand this. But it requires a lot of high-performance processing power, especially if you want to understand the genomes. And it's going to be very important to understand genomes because today we can sequence many, many more genomes than we can process. So today's computing systems are really overwhelmed by the genome sequencing capability that we have. You can see that the cost of genome sequencing has been dropping a lot because the technology is very good in terms of sequencing, but analysis technology, which is computational power, is not good enough today. It's very inefficient. It's very slow. As a result, we cannot keep up with the sequencing technology itself. But it's extremely important to do so because if you, for example, want to understand public health, if you want to predict and figure out whether outbreaks happen before the outbreaks actually happen, and if you want to take preventive actions, we really need to get to the bottom of it and understand genomics much better. So we actually work a lot on genomics, as I mentioned, and this is a recent paper that we wrote. It's an overview paper, so it's actually easy to read, I think. It's a short paper. If people are interested in reading it, they can find it on my website, and they can also find the talk video on my website related to this. And I also give talks about this. They can also find a longer talk related to accelerating genome analysis that I delivered recently at the Technion. And we also have detailed lectures on genome analysis. Since I'm not going to talk more about genome analysis in this lecture, you can find them online in our YouTube channel. So basically, all of this points out to high performance. Basically, we want high performance in the future because we want to solve the toughest and all problems that we are facing. And we are facing even more problems going into the future. Okay, next point is about privacy, privacy and personalization. Basically, going into the future, we want much, much more private and personalized medicine so that we can actually make decisions more easily and in a more personalized manner. Because the medicine is really very much personalized. We have treatments that are general, but if you really want to do the right treatment for the person at the right time, you need to understand that person. You need to understand their genomics. You need to understand their environment. To be able to do that, you need to process a lot of data. Certainly, you need to do the genome sequencing, but certainly you also want to collect data from what they've done and what they've been doing, what their diet looks like, what their exercise looks like, etc., so that they can make a decision. And this is a huge field right now in bioinformatics. How do we enable personalized medicine? And this requires a lot of high performance efficiency, but also privacy, etc. So this is another example where genomics can lead to actually a lot of really interesting insights. These are different species, and you can find the differences and similarities between different species so that you can understand evolution and many other things related to it. You can also understand different outbreaks and different strains of viruses, for example. And this comparative genomics is going to be very important going into the future. It's also called metagenomics. And new genome sequencing technologies that look like this are very important. This is, you can see that you can fit them into your hand. This can make things very portable, as you can see. And we need portability and a small form factor like this so that we can be much more efficient. But again, computational power is lacking, as we show in this paper that we wrote a few years ago. So going into the future, we have a huge challenge and opportunity. We want personalization and privacy in almost all domains: health, medicine, spaces, devices, robotics. For example, in robotics, it's important to become personalized as well, because you don't want a robot that cares to the average person. You want your robot to understand you as a person and to react to you and to be customized to you, as opposed to be customized to a random average sample in the world. So that's why personalization and privacy are very important going into the future. Okay, so this lecture, the past, what I've shown you earlier was actually introduction, but I think that's important introduction. So if you take away something from that introduction, I'm happy. The remaining part of this lecture is really about questioning what limits us in designing the best computing architectures for the future, providing directions for fundamentally better designs, and advocating principled approaches. And I'm going to hopefully cover one or two examples of this, depending on the time, and then conclude. So keep in mind that increasingly demanding applications will always appear. Basically, people are dreamers, and people who actually revolutionize the world are great dreamers, and people are going to continue dreaming. And as long as people dream about new things, they will come. As applications push boundaries, computing platforms will become increasingly strained. As a result, we need to design computing platforms to enable these things. One of my favorite examples over here is Jules Verne, for example. Many of you have probably read novels from Jules Verne, these science fiction type of novels. But they're not science fiction anymore, right? Jules Verne was writing about them in late 1800s. But a lot of the things that he has predicted are coming true or going to come true, etc. So dreamers are all over the world. And it's good to be one of them, I think. So the key realization that I'm going to discuss is that modern systems are bottlenecked by data storage and movement. And focus is going to be on data storage systems, which is memory. So if you look at a modern system, it consists of processing units, memory, and storage. In fact, memory and storage are much bigger than the processing units. And main memory is a critical component of all computing systems. Whatever computing system you're designing, it's a banking system, server system, mobile system, embedded desktop, sensor, it doesn't matter. You need to have main memory. And this system must scale in many dimensions in terms of its size, capacity, technology, efficiency, cost, and algorithms we use to manage it to maintain the performance growth and technology scaling benefits, essentially to design better systems going into the future. And it doesn't matter what kind of infrastructure you attach to this main memory: processors, caches, FPGAs, reconfigurable logic, GPUs, graphics processing units, a combination of all of them, machine learning accelerators, in fact, a heterogeneous combination of all of them, you will be bottlenecked by main memory. Why? Because computing is bottlenecked by data today. And data is really key for many applications. Important workloads are all data intensive. They require rapid and efficient processing of large amounts of data. And data is increasing. We can generate more data than we can process. This is especially seen in AI, ML, genomics, graph processing domains, databases, for example. And memory is really critical for performance in these applications. These are some applications that you may know of: databases, graph processing, data analytics, data centers. And they're all bottlenecked by memory. These are some applications that you may use on your cell phones, for example: web browsing, machine learning frameworks, inference engines, video playback and capture engines that we're using right now, they're all data intensive and they're bottlenecked by memory. And genome analysis, as we discussed earlier, which leads to scientific discovery and medical advancements, is really bottlenecked by memory again. And as you can see, we discussed the new emerging genome sequencing technologies. They're even more bottlenecked by memory going into the future. So memory is also critical for energy, not just performance. And we recently did the study with Google, and we studied the applications that they run on their Chromebooks as well as Android devices. And we found out that more than 60% of the entire system energy is spent on data moment in the memory. And this is a huge number. And this is because, in my opinion, we're designing our systems in a fundamentally bad way that would exacerbate the data moment. So we should actually fix this. Otherwise, we would be wasting a lot of energy in all our computing systems all over the world, because they're all designed based on the same fundamental principle, which is processor-centric. And you need to move the data a lot across the memory hierarchy so that you can accomplish the processing. So we're going to talk about that. We will talk about processing in memory systems as a second part. And we will get back to this work that we did with Google over the course of 1.5 years or so. So memory is also critical for reliability. This is another work that we did with Facebook earlier in 2013, 2015 timeframe. And what we did was we analyzed all of the errors, memory errors, they have in all of their data centers. So Facebook has lots of data centers all over the world. We aggregated all of the data center error information, and we've tried to figure out the reasons for it over the course of more than a year. And we found out that the chip density, memory chip density that employed in the server has a very strong correlation with the failure rate that you observe in the server. So the chip density is how many gigabits you have in your DRAM or main memory chip. And as this becomes larger, you get more failures. Essentially, system reliability is at stake with larger memory chips. Why? With larger memory chips, you get better capacity, better performance, etc. But this becomes more reliable because cells are there are more cells, and cells are smaller. Memory cells are smaller, and they're more noisy, meaning they actually affect each other, and they have reliability problems going into the future. So I'm going to talk about that as a security problem as well. But keep in mind that this is a reliability problem as well, and maintaining reliability costs a lot. In fact, this is Facebook. Okay, maybe you say it's not important, and I would probably agree because it's not life critical in the end, right? But if this becomes life critical, basically, if you employ these chips that are not reliable in your self-driving car, for example, it's going to become much worse. So keep that in mind. So rewording my realization, modern systems are actually bottlenecked by memory today. It's not just data moment and storage. It's really mainly memory. So with that, let's talk about 4 key issues in future platforms. I'm going to talk about security, reliability, and safety, and energy efficiency. We will probably not have time for low latency, AI, ML, genomics. And if I'm going over time, please feel free to stop me, and I will conclude whenever I'm stopped. Okay, so let's start with security, reliability, and safety. Why do we start with security, reliability, and safety? In addition to the motivation that I provided, the infrastructure is all about computing. And if we have security, reliability, safety problems, our lives will be at stake. In addition to that, I will take inspiration from psychology. I did a degree in psychology when I was studying at the University of Michigan during my undergraduate degree. And I was fascinated with why human beings do the things they do. And there's a person, a famous psychologist called Abraham Maslow, who studied that, and he dedicated his life for that study, as you can see from his work that is referenced over here. He is very much famous for this hierarchy of needs also, which is used in many, many aspects of life. It's used in politics, it's used in economics, it's used in psychology, it's used in sociology, etc. So he had widespread influence. And basically what this states is that very simple. It's very principled. Basically, he says that you have to have your basic needs satisfied first before you can think about higher level needs like self-actualization or highest forms of abstract art. Basically, if you're not secure and safe, you're not going to care about something even bigger because you don't have the luxury to care about that because you're threatened at this point. And that's why humans and computing devices are similar, because humans are the ones who are using the computing devices, right? As a result, we need to start with reliability and security. So I already gave you that example of the bridge. I'm not going to repeat that. But basically, we do not want bit flips like this in our critical infrastructure for computing today. And we want safety for these people who rely on computing systems to live their lives. And we want to prevent unforeseen consequences, basically. The problem is today we do not seem to have design principles for guaranteeing reliability and security. That's very unfortunate, and this is very true. Basically, computing platforms we design today, but we don't have design principles for guaranteeing reliability and security. So our goal is to actually provide those design principles and build a methodology to guarantee reliability and security. We're not there yet, but I'm going to give you a story of what we have done so far. As I said, main memory is a big component of reliability and security. As the capacity of a memory chip increases, you become less reliable. So this is also called the DRAM scaling problem. I'm going to go a little bit more technical right now, go low level, and look at a single cell that stores data in main memory. This is dynamic random access memory, DRAM, and fundamentally it stores charge in a capacitor. And it's called charge-based memory because of that. And this capacitor must be large enough for reliable sensing. And you also have an access transistor so that you can access the charge in this capacitor so that you can interpret the value as 0 or 1. And this access transistor must be large enough for long data retention time. So for the memory to work, basically, this capacitor must be reliable, and this access transistor must also be reliable. Now, the problem is, as the size of a DRAM cell becomes smaller, we want that because we want to have more capacity in our memory. We want to make these cells smaller. But as we make these cells smaller, they become more vulnerable to these reliability problems, which will cause security problems, as we will see. So we have been doing a lot of studies to understand these reliability issues with main memory, DRAM, and also other issues also. I'm not going to talk about the other issues, but I'm going to focus on the reliability, safety, security issues. And we built these FPGA-based infrastructures. These are configurable logic-based infrastructures so that we can actually attach memory to them, and we can test memory under many different conditions, for example, different heating conditions. This is another of the infrastructure that we built, and we're making our infrastructures more and more capable going into the future, as you can see. And we open sourced actually this infrastructure. You can see it's in this example. You can actually program this infrastructure using C++. So you don't have to be an expert in hardware to test your memory with our infrastructure. And you can download it and check it. It's used by many people in industry as well as academia, and we're happy to support it. And you can find more information about it in this particular paper, for example. While we were doing our studies, we discovered something that was really fascinating and important. And that is the fact that you can predictably induce errors in most main memory chips, DRAM memory chips today. Basically, you can do this in software. And this is not supposed to happen. Clearly, for a memory chip, you should be able to read and write to a location, but you should not be able to induce errors in locations that you don't have access to. This is not allowed. But we found out that you can do this by circumventing all of the possible protections that you have against memory. Now, this is called the DRAM RowHammer problem today. It's a simple hardware failure mechanism. In fact, it's this first hardware failure mechanism that is proven to create a widespread system security vulnerability. And as a result, people are writing popular articles like this. This is the Wired magazine, which you may have heard of. And an author in that magazine says, forget software. Now hackers are exploiting physics. And this is actually a very nice high-level characterization, very accurate high-level characterization of what RowHammer is about. Basically, hackers can exploit physics to take over your system through software again. So what's the problem? Let me go into a little bit more technical detail. Basically, if you look at memory, memory consists of rows of cells. And if you want to access one row, you need to activate that row. It's called opening that row, or you need to basically apply that high voltage to that row, or the word line, in other words. Now, this high voltage causes some disturbance in the adjacent rows. Now, let's say you do it repeatedly. You say apply high voltage and then close the row by applying low voltage. And then you keep doing this repeatedly. High voltage, low voltage, high voltage, low voltage, high voltage, low voltage, high voltage, low voltage, high voltage, low voltage. And you do this through software commands. Actually, you can do it. You can do it through hardware commands also. But basically, if you keep doing this, we discovered that you will get bit flips in adjacent, physically adjacent rows that have nothing to do with the row that you're reading. And this is not supposed to happen, basically. So we call this row the hammered row, or the aggressor row, and we call these rows the victim rows. And we basically show that you could do this in almost more than 80% of the real DRAM chips that you can buy today. And again, this is not supposed to happen because this row is your application. Fine, you could read or write to your own row. But the other row, you're not even touching it. You're not even reading from it. Just because of the disturbance effect created by this high voltage, low voltage reaction that you're creating, some vulnerable cells flip from 1 to 0. They go from 1 to 0 or 0 to 1. As a result, some critical data may get lost. This may be an operating system page, so you may actually corrupt the operating system. This may be somebody else's private data. You may actually be destroying somebody else's private data in their bank account, potentially. Who knows? If this is happening in a bank, for example, in a banking system, this is very dangerous, again. So basically, all bets are off once you actually start having errors like this in memory. And we said that basically more than 80% of the chips that are manufactured in the world are vulnerable to this effect. And there are only 3 major DRAM manufacturers that dominate the market today. And this is a scaling problem because this problem didn't appear in chips that were manufactured before 2010. The first existence we saw in 2010. And all of the chips that were manufactured between 2012 and 2013 were vulnerable to this effect. So this is a scaling problem. As memory cells became smaller, as they became closer to each other, they became more vulnerable to this toggling, high voltage, low voltage, high voltage, low voltage, high voltage, low voltage toggling of the word line, let's say. So why is this happening? Very quickly, DRAM cells are just too close to each other today. They're not electrically isolated from each other. Isolation is reduced because we want to pack more cells for good reason, capacity. But then we've created a problem also. And access to one cell affects the value in nearby cells due to electrical interference between the cells and wires used for accessing the cells. This is also called cell-to-cell coupling interference. Imagine 2 wires that are running too close to each other. They may interfere with each other, and that's why you don't want wires to be running too close to each other, right? Unless they're isolated. That's why we cover our wires today with isolation, right? But this is not happening in your memory. Okay, so basically when we activate or apply high voltage to a row, an adjacent row gets slightly activated as well. You slightly apply high voltage without knowing this. And vulnerable cells in that slightly activated row lose a little bit of charge. And if RowHammer or this hammering happens enough times, charge in such cells get drained. And basically you lose data that you wrote to those cells. And this simple circuit level failure mechanism has enormous implications on upper layers of the transformation hierarchy. Basically, people later showed that you could actually do many, many attacks through the software. And I will briefly mention those. Why can you do attacks? Because you can actually induce these bit flips with a very simple program that looks like this. This is assembly, x86 assembly language. You can see there's only 6 instructions. You can actually optimize this to be 5 instructions. And we basically, when we wrote the paper, we released the source code as well. Later, Google took our source code and made it better. And this is our source code. And what this source code does, this is a user-level program that selects addresses X and Y in memory such that they map to the same bank. And basically, ping-pongs reads to X and Y. And essentially, by doing this, if the chip is vulnerable, you get errors in the chip. So this is user-level. Anyone can write this program. You don't need special permissions in the system. So for example, if you download a program in your Android, and if it does this, they will basically induce bit flips in your system. And we basically showed that all systems that we tested are vulnerable, Intel and AMD systems, but there's nothing special about Intel and AMD, IBM, ARM, any kind of system that has a good enough memory controller can actually induce these bit flips. So this is a real reliability and security issue. And when we first wrote the paper about this in 2014, we basically said that memory isolation is a key property of a reliable and secure computing system, and access to one memory address should not have unintended side effects on data stored in other addresses. I still believe this strongly. And we said that someone can hijack your computer using what we showed. They could either collapse the system, they could do denial of service, or they could actually take over your system and take all your private data. And while we were showing that, the good folks at Google Project Zero did exactly that. And they basically learned from our work, and they basically showed that they could exploit the DRAM RowHammer problem in software to gain kernel privileges. So very quickly, this is a copy-paste directly from Google's blog post. They basically said they learned about the problem from our paper. They replicated the problem. They showed very similar results to our paper. And they basically built 2 attacks. One attack is very, very interesting. It uses a user-level program which induces these bit flips to gain kernel privileges in x86 64 Linux. And the program has completely 0 privilege. The system is bug-free. And essentially, you can actually have this problem. So very quickly, this is a beautiful security engineering, and I would recommend anyone who's interested in security to read this blog post. But what they were able to do is they were able to induce bit flips in the page table entries of this program so that they could change the permissions that this program has to the remaining part of memory by inducing these bit flips. So these bit flips, normally you don't have write access to a location, right? Because your program is not privileged enough. But if you can induce these bit flips in the right places, you can change the bits that determine whether you have write access And then once the bit changes, now you magically have write access because you flip the bit using the RowHammer attack. And that's the basically key idea. It was able to use this bit flips to gain write access to its own page table. And as a result, you can gain write access to all of your physical memory, and you're compromised completely. And this became famous as the DRAM RowHammer vulnerability. And a famous hacker on Twitter basically said, it's like breaking into an apartment by repeatedly slamming a neighbor's door until the vibrations opened the door you were after. And I think this is also a very nice, beautiful analogy of how RowHammer operates. So clearly, this led to many, many security works later, and there are many security implications. I'm going to go through the security problems very quickly. These folks from Graz in Austria showed that they can basically gain unrestricted access to systems of website visitors by exploiting RowHammer through the JavaScript engine remotely again. And you can read the paper related to it or watch the talk online. These folks from Amsterdam showed that you can do this in Android systems, and they actually released an Android app that can do this transparently. They can gain control of a smartphone deterministically. So you may be running your smartphone as if you know that you're the user, but your smartphone can be taken over by someone through this RowHammer attack these folks developed, and it may be sending messages to somewhere based on what you've done, right? Basically, your private information could be completely at stake over here. These folks show that you could actually accelerate these attacks using GPUs, and you can actually do this again in mobile systems much faster. These folks show that you could actually do this attack in a data center through the remote direct memory access interface. So potentially you could do this in a cloud system where many different applications from many different users are running, and you can gain access to their information. These folks did the same thing, essentially. These folks more recently showed that you could actually leak information. Even if you're not able to take over the system for some reason, you can leak information, leak private information. And these folks recently showed that you can take a deep neural network that is very good at doing prediction and do a RowHammer attack on it. And as a result, this deep neural network's accuracy goes down to very small numbers. Actually, these folks showed something similar, the DeepHammer, as you can see. Before a RowHammer attack, the accuracy of the network was quite good, 90%. After the attack, it becomes 10%. Basically, the network becomes completely useless. So essentially, the whole effort you spent on optimizing your machine learning inference model, machine learning application becomes useless if you have an attack like RowHammer in place. And this is important. As I mentioned earlier, critical infrastructure, right? A lot of self-driving cars rely on machine learning algorithms to detect pedestrians, for example, or detect other cars, or to get input from the user, etc. So if these machine learning algorithms are not secure and they're subject to these RowHammer attacks, they will be extremely inaccurate. So they will essentially be useless. So a future like a self-driving car is not going to be possible if you don't have a secure, reliable, and safe machine learning system that takes into account issues like RowHammer, for example. Of course, other security issues as well. But I think RowHammer is critical because it's a very hardware level security issue that's much, much harder to fix compared to software level security issues. Okay, other folks actually showed other stuff. I'm not going to talk more about that, but this is a picture that I found on the internet. This could be a solution to your worries about RowHammer by breaking your computer, by hammering it. Of course, this is not a good solution, in my opinion. This is a joke, as you can see. So let's talk about the solutions to the problem. So solutions are not easy. At least easy solutions come at a performance and energy cost. These folks, Apple, basically released a security patch saying that they mitigated the RowHammer problem, as you can see, by increasing the memory refresh rates. Basically, they kept reading memory more frequently so that somebody cannot do this attack. Somebody cannot do the hammering enough times before 2 consecutive reads. And this reduces the probability of the problem, but I don't think this solves the problem completely unless you really increase the memory refresh rates by, let's say, 7x or 8x. But it reduces the probability. So it's a reasonable solution in existing systems, but it's not a good enough solution for future. And even in existing systems, in my opinion, if you really want to be completely secure. And I like Apple over here because Apple, when they released their security release, they actually credited our work, as you can see over here. And it's important as a company to credit academic work that you relied on to actually develop solutions. Okay, and other vendors actually release similar patches. I'm not going to talk about that. But basically, I will advocate a solution direction that's much more principled going into the future. We would like to design fundamentally secure computing architectures, and we would like to actually have a system that can predict and prevent such safety issues. So our solution is actually slightly more intelligent. Basically, we call this probabilistic adjacent row activation. And the key idea is very simple. After you activate a row, finish the row activation, you activate one of the neighbor rows with very low probability. And if you do that, you get an extremely good reliability guarantee. And this is very probabilistic. By adjusting the value of the probability, you can vary the strength of the protection. If you're very paranoid, you can increase this probability, for example. And this is actually very low power, very low performance overhead, and stateless, essentially low cost and complexity. And we show that this is an effective solution to prevent disturbance errors. And you can implement in multiple places. I'm not going to talk about this, but Intel actually implemented the solution in its earlier incarnations in their memory controller. This is in BIOS. It's a variant of the solution. We didn't propose in the BIOS, but Intel actually implemented in BIOS. And basically, in the BIOS, as a user, you can choose your RowHammer solution. Either choose hardware RowHammer protection or 2x refresh. And if you choose hardware RowHammer protection, you can choose your probability as we suggested. And I think this was actually a good solution. But unfortunately, what happened in the field was DRAM manufacturers said, oh, we have our own solution. And then they said, basically, now we have manufactured chips that have our own solution inside them, and they're secure enough. They basically advertised DRAM chips to be secure. So Intel turned off the solution, believing them. But that's not a good idea, as we will see in a little bit. Basically, whenever someone says, oh, my solution is secure, but I'm not going to tell you how it is, then it's a good idea probably to question and not believe them. So if you want to know more about RowHammer, these are the lectures, and this is the original paper that introduced the problem. And we have some other papers that talk about the problem also over here, as you can see. Okay, and this is a retrospective paper that we recently wrote with one of my students who did the research with me. So let me talk about what happened in 2020, because this problem did not go away. Because of what I said, DRAM manufacturers said, oh, we have our own solution, and that's secure. But we didn't believe it. We basically investigated the problem, and we analyzed the real DRAM chips, real memory chips in 2020. We analyzed more than 1,500 chips, and we basically show that they're more vulnerable to RowHammer today. There are chips today whose weakest cells fail after only 4,800 activates. This is very, very quick. So someone can take over your system extremely easily today. And chips of this newer DRAM technology are actually even more vulnerable. And unfortunately, mitigation mechanisms are not effective today. So we have a problem, basically. And in this other paper, we showed that DRAM manufacturers' solutions that are advertised to be secure are actually not secure. Basically, we reverse engineered partially their solutions, and we were able to circumvent the solutions that they implemented in their DRAM chips by reverse engineering. And basically, we built attacks that would take over the chips, systems that use these chips, even though the chips were advertised to be RowHammer free. So basically, we proved that DRAM manufacturers were not correct when they said their chips solved the RowHammer problem. So we're back to square one. Why did this happen? Because I believe manufacturers, it's unfortunate that manufacturers resorted to this security by obscurity solution. They basically said, our chips are secure, believe it. But I think they underestimated the creativity of the researchers or other people who can reverse engineer systems. And we were able to reverse engineer the system enough so that we can actually launch these attacks. And we actually did some other work with Microsoft that I will let you read if you're interested. Basically, this work tries to figure out whether you can actually qualify a DRAM chip as RowHammer free, and it turns out that's a difficult problem. But also we developed solutions going into the future. And this is one solution that we have recently published that's very promising going into the future. And I think in the future, we need to develop even more solutions. So if you're more interested in RowHammer, there are a lot of lectures we have. And this is the story of RowHammer lecture that I delivered in a recent workshop at the High Peak Conference as a keynote talk. And I would recommend you take a look at that. There's a lot more research and exploration that can be done. And you may be certainly interested from a practical security perspective. If you're at a company, for example, and if you're worried about the security of your company, you should be worried. And okay, so let's talk about the future a little bit more. Memory is becoming less reliable, more vulnerable. Due to difficulties in memory scaling, other problems may also appear, or they may be going unnoticed. Some errors may already be slipping into the field, just like I showed you. RowHammer is an example. But there may be retention errors, read errors, write errors, etc. And these errors can also pose security vulnerabilities. And we're investigating some of these things, and maybe later I can talk about them. But the problem is actually broader than this. And it's not just about DRAM all memory technologies are actually vulnerable. Some people have actually recently shown that emerging technologies like STT, MRAM, magnetic memory is also vulnerable. Phase change memory has vulnerabilities. Memristors, RRAM have vulnerabilities. Flash memory has vulnerabilities, etc. And if these replace DRAM, either partially or fully, then we're going to have even more problems going into the future. So in the future, we need to keep memory secure. We need to keep hardware secure. We need to keep computing platforms secure completely. And RowHammer is just one example. It's a tough example because this is a hard-to-solve problem. So to be able to solve these problems and keep systems secure, I have a 3-step methodology over here. Of course, I don't claim to understand everything, but I think we need to follow a principled methodology. So first, we need to understand. We need to understand why we're having failures. We need to model them. We need to discover them. We need to predict the failures based on real device data. Second, we need to architect. We need to architect our systems from algorithms to devices, system and memory, so that we can partition the duties across the stack so that we can maintain security, safety, and reliability. And we need to test and design in a principled manner. We need to have high coverage and good interaction with system reliability methods. And we need to keep testing our systems while they're under operation. This is called online testing, for example. And I think that's going to be even more important going into the future. So that's why we build infrastructures that look like this. We want to understand real systems, real devices. And this is our NAND flash, SSD, solid-state drive infrastructure, if you're interested. We have done a lot of work on solid-state drives to understand their vulnerabilities and their issues. And we actually wrote papers about it. And this is a summary paper that was invited to proceedings of the IEEE, where we talk about how solid-state drives today do error handling, mitigation, and recovery. And it talks about what will happen into the future also as the devices become more vulnerable. So if you're interested, you can actually look at it online. And I have lectures on solid-state drives and flash memory. Before I conclude this part, let me talk about 2 other solution directions that are also important. I think new technologies are very important because if we can replace or more likely augment these difficult technologies with a different technology, then maybe we have a solution. Non-volatile memories are an example, but they all have their own problems. So this is still a research area. I think a very promising area, which we proposed in our Dependable Systems and Networks paper in 2014, is embracing unreliability. Basically, we can have heterogeneous memories with different reliability guarantees and store data intelligently across them. Security critical data may go to extremely high cost, but small amount of memory. Non-critical data may go to memory that's very cheap, but we have a lot of it. And I think that's going to be important also going into the future. This is called heterogeneous reliability memory. But I think all of these solutions require co-design across the hierarchy, algorithms to devices. So we really need to be thinking algorithms to devices. So I'm done with the first issue, which is building fundamentally secure, reliable, and safe computing architectures. And as I said, this is going to be much, much more important into the future. It's already important now. So one important takeaway is we need intelligent controllers to actually solve this problem. I briefly mentioned this when I talked about our solution. So let's talk about the second issue, which is energy efficiency. Basically, how do we build sustainable and energy efficient systems into the future? Which means that I think we need to think about our systems to become more memory-centric. So again, I'm going to talk about Abraham Maslow, because if you really think about what Abraham Maslow said about humans, look at that. Security and safety are the second part. It's really all about physiological needs first. Basically, if you don't have energy, maybe you don't care about your security and safety because you're dead anyway. So basically, you need to have energy to begin with. Maybe energy is more fundamental than security and reliability and safety. So basically, I think I will show this picture again. Do you want a future that looks like this? Beautiful, sustainable, or like this? I will argue that we want the best of all worlds, meaning we want energy efficiency and sustainability, but we also want high performance and productivity. So the problem is that our current design principles are not good enough to enable that. Data access is the major performance energy bottleneck in our systems today. And our current design principles cause great energy waste because we're moving data all around. And to tolerate that data movement, we actually add a lot of hardware and software so that we can reduce the performance loss. But this causes even more energy waste. So we're in a vicious cycle today, basically. We keep increasing the energy and power consumption and the complexity of our systems so that we can tolerate the data movements, adverse effects. We need to get out of the cycle. And in order to be able to get out of that cycle, we need to understand the problem at the heart of the problem, which is processing of data is performed far away from the data today. So if you look at a computing system, this is von Neumann, by the way, and he is the person who enabled von Neumann model and the computing systems that we design today, which has worked really well. But going into the future, we may want to think about it again. So basically, there are three key components of a system: computation, communication, and storage and memory. And we have heavily optimized the computing unit today because today's systems are very processor-centric. Basically, data has to move to the processing unit before it can be processed. Processing unit can be a CPU, GPU, FPGA, machine learning accelerator, etc., vision accelerator. It doesn't matter. Data has to move there first. Data cannot be processed inside the memory unit. And that's the problem. All data is processed in the processor at great system cost, and data storage units are dumb. Yet we know that the problem is in memory. So this is a paper that was written by Dick Seitz, who was the chief architect of alpha processors. After their team designed the fastest alpha processor, fastest processor of its time, he wrote this one-page article in Microprocessor Report saying that it's all about the memory. Stupid. Essentially, he said that we designed this processor. It's one of the fastest of its time. It's able to finish 4 instructions per clock cycle, but it's finishing 1 instruction every 5 clock cycles on this important data-intensive workload. Why? It's waiting for data almost all the time. And he basically concludes the paper saying that I expect that over the coming decade, memory subsystem design will be the only important design issue for microprocessors. Okay, fast forward 10 years. This is data from my own first paper, scholarly paper, that was published in 2003. That's part of my thesis, PhD thesis. And we basically worked with Intel and looked at all of their workloads and showed that the processor, a state-of-the-art processor, is waiting for data to come back from main memory for more than 50% of its time. So it's not doing useful work otherwise. And you can read this paper if you're interested. This is my first paper that I've ever written, so I'm proud of it. You can take a look at the data that I showed you inside that paper if you're interested. Okay, you don't believe me, maybe. You don't believe Dick Seitz, but maybe you believe Google. A lot of people believe Google today. I don't know why, but they are believed. But they actually did a very similar study recently in 2015, and they basically showed that in all of their data center workloads, you can see Gmail, for example, here, search, video. You can guess what those are, Hangouts, for example, ads, etc. Basically, they showed that most of the time, the processor is waiting for memory. This is a state-of-the-art processor. And they actually do a lot more studies, and you can take a look at them. Basically, we have a problem. We have a processor-centric design. It's grossly imbalanced. Processing is done on only one place. Everything else just stores and moves data. As a result, data moves a lot. We waste a lot of energy. We waste performance, and the system becomes complex. So to tolerate this, we make systems even more complex and bloated. We add mechanisms to tolerate data access from memory in hardware as well as software. We have complex hierarchies, caches, more levels of caches, prefetching mechanisms, multi-threading, out-of-order execution, etc. This makes the system more energy inefficient, low performance, and complex, especially when these techniques are not good enough. And as a result, we have a picture that looks like this. This is my cartoonish hand-drawing picture of an existing computing system. And you can see that most of the system is dedicated to storing and moving data. So if you do the calculation, more than 90% of a chip and a node is dedicated to data storage and movement units. We call these computing systems, but the hardware real estate of these systems is really very small that's dedicated to computation. So let's talk about the system strengths, higher level strengths also. Applications today are increasingly data hungry, as we discussed earlier. So data access is a major bottleneck. Energy consumption is a key limiter of all systems, and data moment energy dominates computation energy. So we're going to look at this especially in a little bit. This is especially true for off-chip to on-chip moment. Let's take a look at data moment versus computation energy. This is slides that I borrow from Bill Daly, who is the chief scientist of NVIDIA today. And basically, in this slide, he shows the relative energy cost of different operations. So this is a 64-bit double precision floating point operation. It's a complex addition, let's say. It's only 20 picojoules, whereas a memory access is 16 nanojoules. That's 800 times more costly. So basically, today, a memory access consumes 2 to 3 orders of magnitude more energy of a complex addition, which is not good. So the question to ask over here is, does it really make sense to do multiple memory accesses and bring the data in to a unit that can do very efficient computation? Maybe it doesn't make sense. Maybe we should really be doing the computation inside the memory so that we don't move the data, because the energy cost of data moment is extremely high, and most of the energy cost is spent on data moment when moving the data. Okay, I'm going to skip the slide because they show essentially the same thing with some references. As a result, we have a picture that I showed you earlier, more than 60% of the entire system energy in a mobile system that's designed for energy efficiency is spent on data movement. I'm going to get back to this work later on. So basically, I will argue that we do not want to move data. So to be able to do that, we need a paradigm shift, though. We cannot do it easily. We want to enable computation with minimal data movement, compute where it makes sense, where data resides. It could be in memory, it could be in storage, it could be in disks, it could be in tape, it could be in the interconnect, it could be in the network. But wherever data resides and wherever it makes sense to minimize energy and maximize performance. Basically, we want to make computing architectures more data-centric. So our goal is to enable processing inside the memory. So memory has a lot of capacity today. We can store big applications like databases, graphs, media. You would like to be able to query the memory, ask questions to it. Memory, can you execute this function for me? Memory says yes and returns the results. That's beautiful. Today, you cannot do that. Today, memory is very dumb. Memory has to supply data. But memory is going to be an active component of computation going into the future. So there are many questions over here. How do you design the compute-capable memory and the controllers? How do you design the processor chip and in-memory units? How do you design software and hardware interfaces? System software, compilers, and languages, and applications, algorithms, and theoretical foundations. So it's an entire stack problem, as you can see, all the way from algorithms to devices. And it's a very exciting problem. There are many, many problems inside every part of this stack. And we need to solve these problems. But we can also start step by step. So let's start simple. I'm going to give you very simple examples of success in data-centric computing systems. And one example is data copy and initialization. So if you've written a program, you probably know that you need to initialize things and you need to copy things. And this consumes a lot of time in many applications. In fact, Google, in the paper that I mentioned, showed that memmove and memcopy system calls consume about 5% of all of the execution cycles in their workloads. That's a lot for just 2 system calls. So clearly, there are many use cases for large data copy and initialization, as you can see in the slide. How do we do data copy today in today's systems? Basically, if you want to copy the source page to the destination page, we go through the processor, which is a bad idea, as you will see. Basically, you bring the source page byte by byte into the caches. You bring the destination page byte by byte into the processor chip, the caches, and then you do the copy, and then write the data back. This is high latency, clearly, because you move data a lot. This is high bandwidth utilization on the memory bus, which is the most important resource in the system. This causes cache pollution, and this causes unwanted data mode, because you may be initializing a 1 terabyte database, for example, and then you're not going to use the data anytime soon. So you're bringing this data all the way into the caches unnecessarily. There's no reason to do this. So for a 4 kilobyte page copy, by doing this through the memory controller, it takes about 1,000 nanoseconds and 3.6 microjoules. I'm going to show you a mechanism that's going to improve this by more than an order of magnitude in both cases. And the mechanism is very simple. It's called in-memory copy, row clone. And if you ask the question to a child, like let's say 10 years old, and if you say, I'm doing this copy inside the processor, is it a good idea? They will probably say, why don't you just do it in memory? And that's the idea, basically. Do the copy inside the memory. This is low latency, as I will show you in a little bit. This is low bandwidth utilization, no cache pollution over here, and no unwanted data. And as a result, we get more than an order of magnitude improvement in energy, latency, and almost 2 orders of magnitude improvement in energy. And the idea is row clone. Very quickly, I will go into a little bit more detail. And the basic idea is 2 activations in memory. So if you look at memory, it consists of rows, and there's a row buffer. Everything has to go through the row buffer to be able to be read. The idea is to first activate row A, which brings the data into the row buffer. And then you consecutively activate row B, which implicitly deactivates row A. But the data is in the row buffer, and you basically move the data from the row buffer into the destination row when you do the second activation. So this is how DRAM operates. We're not changing the principles of operation. You can actually do this in real DRAM chips by violating the timing parameters, but you can actually do it more reliably by designing the system with little modification. Basically, it's negligible hardware cost. And what you gain is significant. More than 10x improvement in latency and more than 74x reduction in energy. And ignore these bars. Basically, we solve these problems later on, and I'm not going to talk about those papers that solve these problems. But this is the row clone paper that enabled this idea. And later, many folks have demonstrated that this idea works, and it can actually get significant system performance and energy improvements by doing this on a real system. So basically, we're thinking of memory as an accelerator. We're adding specialized capability inside the memory as to what the memory is good at. So memory is really good at, for example, copy and initialization. That's great. We're going to do copy and initialization inside memory. So we're very good at designing all sorts of accelerators today. like CPUs, small CPUs, large CPUs, video cores, imaging cores, machine learning accelerators, GPUs, vision accelerators, pedestrian detection accelerators, etc. But we can treat memory similar to a conventional accelerator, and we want accelerators on the memory side. All of these accelerators are sitting on the this side. We should probably be putting accelerators over here. Yes. Okay. Okay. So I'm going to finish in 5 minutes. Is that okay? Okay, perfect. Okay, so I'm not going to talk about this in more detail. Very quickly, we can support other operations as well at low cost using analog computation capability in memory. And you can get basically similar performance energy improvements, 30 to 60x, as you can see. And you can read this paper in more detail if you're interested. And new memory technologies can enable even more opportunities, actually. If you're interested, you can watch my lectures that I'm going to refer to. But basically, this is an example from a real database application. So you can actually have improvements of 4x to 12x in terms of latency of the queries that you do in a real database if you do the processing inside the memory chips. And these results are reported in this paper. This is another paper that we wrote related to IEDM bulk bitwise execution engine. And there's another paper coming up that shows how to do this end-to-end very soon. Let me give you one more example. I'm going to focus on results. Graph processing is everywhere. It's used by many works and companies, as you can see. And the key bottleneck, again, in graph processing is memory, because you have frequent random memory accesses and little amount of computation. And one way of tackling the bottlenecks is doing computation very close to memory. So this is an emerging technology. It's called 3D stacked memory technology. You have memory layers and computation layers. Basically, you can do computation inside this logic layer. And other true three-dimensional technologies are under development as well. Basically, we designed a system called Tesseract that can actually do the computation. I'm not going to go into the details because we don't have time, but you can read this paper for more detail if you're interested. And what this shows is that you can actually design a system that's scalable, that looks like a GPU, where you ship the computation to the cores that are hosting the data that you're manipulating. So here we minimize the data movement. We ship the functions to the data. And if you do that, you need a different programming model, and you need actually special mechanisms. But your system looks very different. Basically, these are the state-of-the-art systems on the left. There's a dichotomy between memory and processors and memory. In our case, you cannot distinguish where the processor and memory is, as you can see, because they're all together. And as a result, you get very high bandwidths available to the memory, 8 terabytes per second. Right? And as a result, your performance improvement on real graph processing, graph analytics, is close to 14x, as you can see. And your energy reduction is more than 8x. And you can read this paper for more detail if you're interested. Okay, so I'm not going to talk about the remaining work over here. I already mentioned we did this work with Google, where we were more realistic. And we basically showed that you can improve performance by 2x in real systems with little effort by offloading simple functions to memory. I'm not going to talk about that in more detail, but you can see that we actually improved TensorFlow machine learning applications significantly. And you can read this paper for more detail. We do a lot more work on processing in memory. I'm going to go through these relatively quickly because I didn't intend to talk about them. But for example, we have a string matching accelerator that's good for genome sequence analysis, and another accelerator for time series analysis, and also weather prediction models as well. But basically, in the end, we need to revisit the entire stack, but we can get there step by step. If you're really interested in processing in memory, I would recommend watching or reading this work that we have recently written. And another work also is there. But the good news is there are actually companies that are building these systems that we envisioned in the past. As you can see, Samsung is one of them. Opmem is another one of them. And you can see the chip implementation. You can also watch our lectures online if you're interested. And there are many of these lectures. And one tutorial that I delivered in the IEDM conference, which is the top conference in electron devices, it could be interesting. And you can find it online as well. So basically, this concludes the second part of my talk. We have a huge challenge and opportunity for the future, fundamentally energy efficient computing architectures, how do we build them, and data-centric computing architectures, how to enable essentially processing in memory. Okay, so I think I'm almost done. Let me conclude with the concluding remarks over here. The rest of the slides are for your benefit. I said I'm going to skip them anyway, so I'm skipping them. But let me do the concluding remarks in 2 minutes quickly, and then we will be done. Okay, so I think this is a fun part of the talk. Basically, there's a famous architect who said architecture should be designed based on principle, not upon precedent. And this was Frank Lloyd Wright, who was a famous American architect. who did not design this, because this is a precedent-based design. It's okay, it works. But his principles led him to design this. And this is a masterpiece today. It's called Falling Water. It's very close to Pittsburgh, where I used to teach at. And it's beautiful, as you can see. There's a lot of good principles that went into it. Now that I'm in Zurich, I give examples of train stations. This is a precedent-based design. What came before, it's okay. It's not bad. But it's nothing like this. This is a Bahnhof Stahlhofen in Zurich. And this is in Lisbon, the same architect. This is in Valencia, the same architect. And this in New York, the same architect. And all of these are examples of principal designs, different thinking, creative thinking, and basically changing the level of our thinking and creativity to a new level. And I think these architects were very successful at that. What they built came at a cost, but every new innovation, every new paradigm change comes at a cost. You have to pay the cost to change the paradigm and start playing at a different level. So overarching principles of computing, do we have them? I do not believe we know them fully yet, and I don't claim that we know all of them, but I certainly think that processor-centric design cannot be the single principle. This brain over here is a distributed system that's processing and doing memory at the same time. So I think we need to rethink the principles, and we need to exploit good principles, some of which are provided here, but we need to develop new principles as well. And more than anything else, we need open minds for this. So to conclude, it's time to design principled computing architectures to achieve the highest security, performance, and efficiency. We need to discover design principles for fundamentally secure and reliable computer architectures. We need to design systems to be completely balanced and energy efficient to enable data-centric systems and low latency systems. And we need to enable new platforms for genomics, medicine, health, artificial intelligence, and machine learning. And doing so can lead to orders of magnitude improvements, as I showed you in this talk. We can enable new applications and computing platforms, and we can enable a better understanding of nature and our origins as well, and who knows what else. So I think the future is very bright, regardless of all the challenges, but we need to think differently. We need to think across the stack, but we can get there step by step as well. And again, if you're interested, I'd recommend you take a look at these talks as well as papers. And I will acknowledge people who fund our research. There are many of them, as you can see. And I'll acknowledge my students whose work has contributed to all of this talk. And you can read our newsletter for a lot more information about other research that we are doing. So with that, I will conclude. Thanks for bearing with me. I'd be happy to take any questions.